Well, welcome to chapter 13. And in this chapter, we're going to discuss the topic of heat. Now, maybe you haven't thought much about that. What is heat? If I were to ask you that question, how would you define it? It actually is one of those things that we have a sense of it, right? We using the word sense, like literally with our senses, we can feel heat. But how would you define that? What is it? And this is actually a topic that puzzled natural philosophers. In the 1700s, they actually thought heat was a gas. They had a name for it. They called it a caloric, C-A-L-O-R-I-C. And like I said, they said it was a gas. So if it was a gas, that meant it was matter. And that was kind of the accepted view until the 1800s, until this guy came along named James Prescott Joule. And Mr. Joule had done some experiments, and he had shown how energy could be used to produce heat. And in showing this experimentally, he did not believe that heat could then be matter, because if energy gave way to heat, then it meant, if energy gave way to matter, then it meant that we could destroy energy and actually create matter. And this conflicted with his deep-held Christian beliefs, which said that God alone was the creator, that man couldn't create. We could cause things to change form that God had already made, but to go from energy to something that was matter would mean we could create matter. And so he set out to disprove that, and he did indeed, and he basically showed that heat was actually just another form of energy. So we need to define what energy is as we begin this discussion. And in this chapter, you'll see me sometimes use energy and heat interchangeably, right? Because heat is just a form of energy. So what is energy? Well, I've got that definition written up here for you first. And energy is simply the ability to do work. The ability to do work. And we use the unit of joules to measure energy. So you'll see that as we're doing our math problems in this chapter. Of course, if we're going to say it's the ability to do work, then we need to define work. So what is work? Well, the next definition tells us that. It's the application of a force to move an object over a distance. So you apply that force and it causes movement of the object, right? And so that's what we call work. And if we have the ability to do work, then we say that is energy. Now, heat specifically is the energy that is exchanged because of a difference in temperature or a change in phase. So we're gonna look at some mathematical equations that give us the ability to calculate heat in both of those instances. And I want to, as a part of this discussion, I want to define a term that we're familiar with. We are familiar with the term calorie, right? Now, when we think of calories, we think about what's listed on the back of our food packages, right? Along with the nutritional information, how many calories a particular product has. This calorie here is little c calorie. The calories on the back of food packages is a capital C calorie, but a little c calorie, which is what we're going to use in chemistry, it is the amount of heat that is required. So amount of heat required to raise 1 gram of water, 1 gram of H2O, 1 degree Celsius. All right, so specifically, water. It has to do with that substance, and it is the amount of heat required to raise 1 gram of water 1 degree Celsius. By comparison, a food calorie, which is a capital C, 1 food calorie, right, food, is equal to 1,000 little c calories, which again, what we use in chemistry. All right, so those are just some definitions, some things that we need to make sure that we understand so that the rest of our discussion makes sense. Just to put this value in reference, all right, if we think about the calories that are on the back of our packages. So, you know, when you see like there's percentages on the back and the nutritional information, it'll say this is 20% of your daily allowance or whatever. And all of that, it'll say that this is based on a 2,000 calorie diet. That's usually what those values are based upon on the back of our food packages. So if we had 2,000 calories, right, a typical daily diet, that would be enough energy to raise 5 gallons of water 100 degrees Celsius. So that's actually pretty impressive, right? If we could raise a gallon of water 100 degrees Celsius, that means we could boil 5 gallons of water with what we consume in food in just one day, right? So that's pretty amazing. Now, one thing that we do also want to know, if you'll look at, actually, no, we're not going to go there quite yet. That's going to be our next topic. But I do want to point this out. In terms of joules, since we said that we're going to think of joules, we're going to use joules as our energy or our heat unit in this chapter. 1 calorie, little c chemistry calorie, is equal to 4.184 joules. All right. And if you need that on a test, I'll give you that. You don't have to memorize that. But just something for you to be aware of. You actually are that. I'm being a little bit deceptive. I'm not meaning to be, but even though you don't have to remember that 1 calorie is equal to 4.184 joules, we're about to see that number 4.184 in another scenario, and you are going to need to memorize that. So let's go ahead and move on to that next topic. What is that next topic? The next topic is specific heat capacity. All right, so what does that mean? Specific heat capacity. You'll also hear it referred to as just specific heat. But specific heat capacity, it is the amount of heat this is going to sound very familiar, the amount of heat required to raise a specific mass of a substance guess what? We're going to raise the specific mass of that substance 1 degree Celsius. Sounds a lot like when we were talking about calorie, right, in the previous section. We said a calorie, a chemistry calorie, is the amount of heat required to raise 1 gram of water 1 degree Celsius. So a specific mass, in this case 1 gram of water, that substance, 1 degree Celsius, to raise that is called a calorie. All right, but if we want to talk about anything, any substance in general, specific heat capacity gives us a sense of of how this substance heats up. Okay, so it basically tells us how easy or how hard it is to heat up a particular substance. And we have a chart on page 392. And that chart shows us the specific heat capacities of various substances. And there's one specific heat capacity in particular that I want you to memorize. You don't have to memorize the rest. If you need any other ones, I want you to, I will give you that information, all right? But for water, the specific heat capacity of liquid water, right? Notice in the table it has an L out next to it, of liquid H2O equals 4.184, right? There's that 4.184 number again that we saw just a second ago. 4.184 joules per grams degrees Celsius, all right? So grams and degrees Celsius is on the bottom of that fraction there, and joules is on the top. All right, so I need you to memorize that. Make sure you know that. For H2O, the specific, that is so hard for me to say for some reason, the specific heat capacity is 4.184 joules per grams degrees Celsius, all right? And again, it tells you how easy or how hard it is to heat up a particular substance. The higher the specific heat capacity, the harder it is to heat up that substance or to cool it down, all right? In other words, the harder it is to change its temperature, all right? So water is actually pretty high compared to the other substances when you look at at this table that we have here on page 392. For example, brass, 0.38, right? Joules per grams degrees Celsius. So much easier to heat up and cool down brass than it is water. Pretty interesting stuff, right? So how are we going to use this? Well, specific heat capacity is going to come into play as we begin to measure heat. And I'm going to give you a formula that you need to know. And that formula is Q equals M times C times change in T. All right, what is this? If I ask you how much heat it takes to do something in particular, This is a formula that we'll sometimes use to figure that out, all right? And so in this formula here, Q is heat, or like I said, we'll use energy interchangeably with heat in this chapter. So if I ask you for how much energy is required or how much heat is required, then I'm asking you to find Q, okay? M is, it's a letter that we're familiar with in chemistry, but we've seen it mean different things, right? Most recently, we saw little m to stand for molality, right? When we were looking at concentrations. We also know that little m is the value that we use for meters if we're measuring length and using the metric system unit. But in this case, it's what we saw m to stand for at the very beginning of the course, which is mass. We said that m stands for mass. Remember when we were calculating density, we used little m for mass. So that's going to be our mass. And this little c here is, even though we just said that calorie is a little c calorie, this is not calorie. This c here is the specific heat capacity. So for the substance, whatever substance we're talking about, this is little c is the specific heat capacity of that substance. And then change in T, as you might suspect, is the delta T means change in. This is the change in temperature. All right. So that's the formula we're going to use for calculating heat, one of the formulas, and our first formula in this chapter. Now, when we want to find the change in any value, how do we do that? Well, if you think about it, if I said the temperature was a certain value at the beginning of the day and by the end of the day it was a different value, and I asked you to tell me what the change in temperature was, what would you do? Well, you would take whatever that final value of temperature was, and you would subtract from it the initial value of that temperature. So if our day starts off and it's 60 degrees, and by the end of the day it's 91, and I asked you what was the change in temperature, you would say it was 31 degrees because 91 minus 60 is 31 degrees, right? So that's exactly the formula we'll use for change in T. Change in T is the final temperature, T sub F here, minus the initial temperature, T sub I, right? So just make sure you know how also to find the change in temperature because we'll be doing that in these particular problems. All right, so as is often the case, it's easiest to understand what these equations are all about just by doing an example, right? So let's do an example. Our example is on page 394, it's example 13.1. And if we look at that example, it says we have a 500 gram block of copper. And it starts out at 51.2 degrees Celsius and cools to room temperature, which is 25 degrees Celsius. How much heat did it lose? And they give us the specific heat capacity, little c, for copper, which is 0.386 joules per grams degrees C. So we're trying to figure out the amount of heat that it lost. And what did we say Q stood for? It stood for heat or energy. Sometimes you'll see the question presented to you. It could have just as well said, how much energy did it lose? And it's asking the same exact question, right? So the formula that we just used was Q equals M, or that we just learned was Q equals M times C times change in T. And they give us all of that information in this problem here, right? What is the mass of the block of copper? They tell us at the very beginning that it's 500.0 grams, right? So that's our M. What is the C, the little c? They give us that as well. They tell us that it's 0.386 joules per grams degrees C, right? And then finally, they give us a starting temperature. It starts out at 51.2 degrees Celsius and a final temperature. It cools down to 25 degrees Celsius. So we said to find the change in T, you take the final temperature, which is 25 degrees Celsius, and you subtract from it that starting temperature of 51.2 degrees Celsius. And we just do the math with that, right? We simply plug in those numbers. Once we do that, notice what's going to happen. Based on this little c unit right here, this grams is going to cancel out with the grams in that value. And we're going to get when we do the subtraction here, we're going to get a value of degrees Celsius. And so that's going to cancel out with degrees Celsius here. And so we're going to end up with a value of joules, right? That is what our energy or our heat unit is going to be. And so when we do the math for this, we're going to end up with a value of negative 5,000. They've done some rounding here in the book based on significant figures, but negative 5,060 joules is how much energy was lost when that block of copper cooled down. Now what you see with this is that if Q is negative, that means energy was lost. All right. If it was positive, then it means that it actually gained energy in that case, right? So technically, the answer is not negative 5,060 joules because they said how much heat did it lose. We would say, well, it lost 5,060 joules of heat. That would actually be our answer. The negative sign is what tells us that it was energy that was lost rather than energy that was gained. Okay? So that would be the correct answer to the question. Just to make sure we understand it, why not do one more example here. It says to work on a 350 gram iron horseshoe. So we're given another mass, 350 grams. A blacksmith adds 59 kilojoules of energy to it. So 59 kilojoules of energy. What is our variable that we have learned for energy? It's Q, right? So Q equals 59 kilojoules. And if the horseshoe started out at a temperature of 22 degrees Celsius, our initial temperature was 22 degrees Celsius. What is the final temperature? And they also give us the little c. The specific heat capacity of this iron horseshoe is 0.44 joules per grams degrees C. Now, this number here, the specific heat capacity, is always going to be given to us in joules per grams degrees C. And so what that means is that everything that's in every number that we plug into our equation, the units have to match the units in this value here. So when we look over the units that they've given us, we see immediately that this thing here is not in joules. It's in kilojoules, right? Over here, this says we need a unit of joules. So we're going to have to convert that from kilojoules to joules. We're going to do the same thing that we've done in the past. If we converted from like when we were finding concentration, we went back and forth between grams and kilograms when we were dealing with molality. What we learned is if we're going from grams to kilograms, we have to move our decimal place 3 places to the left. But 3 places to the left would be that way for you, I guess. But if we're doing if we're going the opposite direction, if we're trying to go from kilograms to grams, then we would have to move our decimal place 3 places to the right. And so in this case, we're going from kilojoules to joules. So we're going to move our decimal place 3 places to the right and say that this is, even though it's 59 kilojoules, or since it's 59 kilojoules, that makes it 59,000 joules. All right, so that's the number that we're going to have to plug into our equation. Now, this time we're not finding Q, they gave us Q, right? We're still going to use the same equation, Q equals M times C times change in T, but we're actually trying to find, not change in T, but we're trying to find the final temperature, right? What's unknown here that they're asking us to give is what TF is. So what is TF? That's what we're trying to find. So what you could do here is, let's take this equation and solve it for change in T. Rearranging this equation to solve for change in T, we get that change in T is equal to Q over M times C, right? That's just algebra. We're just divided both sides by MC, and they cancel out on the right side, and on the left side we have Q equals M divided by C. And so plugging in those values, 59,000 joules divided by a mass of 350 grams. That mass is fine. They didn't give it to us in kilograms. It's in grams, which is what we want. And little c is 0.44 joules per grams degrees C. That gives us a change in T value of, looks like 380 degrees C. All right, that's how much the temperature changed. That's not what we're trying to find, though. We're trying to find the final temperature. So again, what is our change in temperature formula? It says that change in temperature equals final temperature minus the initial temperature. So again, algebraically, if I rearrange that, that says that the final temperature is equal to change in T plus the initial temperature. So plugging in those values, Our change in T value is 380 degrees Celsius plus the initial temperature, which they told us was 22 degrees Celsius. And so we get a final value here of 402 degrees Celsius. That is our final temperature. Let's make sure that agrees with what we have in the book. Oh, in the book they changed it to scientific notation and said it was 4 times 10 to the second power degrees Celsius. Why did they do that? Because again, they are worried about significant figures. We're not worried about like that the way that they are. I told you guys we weren't going to stress over that. So we're going to just leave it at 402 degrees Celsius. You would get credit for that answer. Okay? All right. Well, one last thing that I want to look at in this particular section here is calorimetry. And what is calorimetry? Well, calorimetry, we use a calorimeter to determine what the specific heat capacity is of a substance. And we've got a picture of a calorimeter on page 395. It is simply the picture that they've shown us here is that we have a cylinder, right? Looks something like this. Inside that cylinder, we have a substance, a block of something that they've dropped down in there, and we're trying to figure out what the specific heat capacity is of this substance that we've dropped down in there. And so you'll notice in the drawing here that there's a thermometer. We're going to try to. So our thermometer's coming through the top and all the way down into the water, right? So there's a little portion down here that's measuring the temperature, and we're reading it on this part that's sticking out of the top here. And notice that they show this little fan that comes down in here, and my fan's probably not going to look as good as theirs, but there's this little fan in here, something like this, right? And that fan is basically stirring up the water that's in, or whatever liquid, but in most of our examples that we use, we're going to see that the liquid that's inside here is water. And so that fan's stirring up the water. And so basically you take this object here, that's of some substance, maybe it's iron, or maybe it's stainless steel or something like that. You heat it up, and you know what the temperature is of the water inside the calorimeter. You drop this object inside the calorimeter, and you measure the change in temperature as that object cools down. And so when it cools down, you're going to have a final temperature of the object as well as the water in the calorimeter. Now here's the thing with calorimeter experiments or calorimetry, the object, when it cools down, whatever the final temperature is of the object, it's also the final temperature of the water. So we're going to basically have a couple of initial temperatures here. We're going to have the initial temperature of the water. We're going to have the initial temperature of the object. But when you drop the object down in there and it begins to cool down, it's going to be heating up the water, and it's going to level off, and those things are going to be at the same final temperature at the very end. Okay, so that's important for us to keep in mind so that we know how to do these calorimeter calculations. Now, with calorimetry experiments, let's see, we need a new formula, and that new formula is this. The negative Q of the object. So in other words, if we figure out the heat for the object, the negative heat for the object is equal to the Q of the liquid plus the Q of the calorimeter. All right? So that's the formula we're going to use. We're still going to use our Q formula that we had before to calculate Q for the object and Q for the liquid. But we have a new formula that we're going to use for the calorimeter, and that formula is Q equals, for the calorimeter, and this is only for the calorimeter, for nothing else, all right? This is the only time we will use this Q. Q for capital C calorimeter, actually I'm just going to write it like this, C-A-L. Q for the calorimeter is equal to capital C times change in T. Now, what is this capital C? This is the heat capacity, not specific heat capacity, the heat capacity of the calorimeter. All right, how are you going to know that? You'll only know that if I give it to you. Okay? So when we do these calorimeter experiments, when you have problems related to the calorimeter experiment, if you need the heat capacity of the calorimeter, I will give it to you in the problem. Sometimes these problems will say you can ignore the heat of the calorimeter. So what that means is that when we're using this formula over here on the left, we can just throw that value out and simply say that the negative Q of the object equals the Q of the liquid, okay? So, but if we have to include the Q for the calorimeter, we're going to use this formula right here for that. Again, I'll give you the change, the capital C. Another thing to keep in mind is that when we talk about the temperature change for the calorimeter, the temperature change for the calorimeter will be the same as the liquid that's inside the calorimeter. So whatever the initial temperature is of the liquid, it will also be the initial temperature of the calorimeter. And whatever the final temperature is, well, I told you in calorimetry, in these calorimeter experiments, everything has the same final temperature, all right? So it's just that initial temperature there will be different for the object than it will be for the liquid in the calorimeter, okay? All right, so let's do one of these problems, again, making sure that we understand how we might use this. And we've got an example on page 396, example 13.2. And they tell us we have a sample that is 45.9 grams, that has a mass of 45.9 grams. So the mass of our object in this case is 45.9 grams. And it's an unknown metal, and it's heated to 89.7 degrees Celsius. Now, how did we say this works? You heat the object first, and then you drop it down into the calorimeter. So this, if whatever it's heated to start with, that's the initial temperature of the object, all right? So I'm gonna write that down right here, Ti. Actually, let me do this. I'm just gonna say this is my object column, all right? And so this is the Ti for the object, and that has a value of 89.7 degrees Celsius, all right? It's dropped into a calorimeter that contains 150 grams of water. So now we're talking about the liquid, right? This is the liquid in the calorimeter, and we're given the mass of that liquid to be 150 grams. And the initial temperature of the water is 25 degrees Celsius. So it's got a different initial temperature than the object does over here in our other column, right? Let's put a little line between these two so we see that there's two columns there. The initial temperature of the water is 25 degrees Celsius. Now, by the end of the experiment, the temperature increased to 26.9 degrees Celsius. So the water at the end is 26.9 degrees Celsius, right? That's our final temperature for the water. What is the specific heat capacity of the metal? We can ignore the heat absorbed by the calorimeter. So they told us we don't have to worry about the calorimeter this time. So that means the formula that I gave you where we had the negative Q of the object, what it's equal to, in this case here, it's only going to be equal to the Q of the liquid because we don't have to worry about the calorimeter. We can ignore that for this particular experiment. What they want us to find is little c for the object here, right? That's the unknown. And they didn't specifically say the final temperature for the object, but what is it? Remember, in calorimetry experiments, they're all the same things. So everything in it has the same final temperature. So the final temperature for the object is going to be the same as it was for the water, 26.9 degrees Celsius. Now, we have enough information over here. That's not true. We're trying to find little c. Hang on just a second. We almost have enough information over here to find the Q for the liquid. What are we missing? Well, we're missing the C for the liquid, right? Because remember, our formula for Q is Q equals M times C times change in T, right? So we're missing C. Well, what is the C for our liquid? They didn't give us that. But what they did tell us is that our liquid in the calorimeter is water. And I told you guys earlier, you've got to memorize that. So remember, little c for water is 4.184 joules per grams degrees C. So we know that as well. So now we can find out the Q for the liquid, this right here, which will allow us to find the Q for the object, this right here, and then we can use the Q for the object to figure out what C is for the object, which is actually what they asked us to find. All right, so that's the path we're going to take. Let's see if we can do that. Let's calculate first the Q of the liquid. The Q of the liquid equals mass times specific heat times change in T. So plugging those values in, we have 150 grams, 150 grams times 4.184. I'm not going to write down that whole unit just for space reasons, times the change in T, which is the final temperature, 26.9 degrees Celsius, minus the initial temperature, which is 25 degrees Celsius. And we plug all of that in and we get a Q of our liquid, which is 1,200 joules. Again, rounded. They're going to round it in the book for significant figure's sake, right? So now we have the Q of the liquid. Well, according to this formula right here, whatever the Q of the liquid is, the Q of the object is the negative of that, right? And so the Q of the object then is negative 1,200 joules. Now again, if they had not said we could ignore the calorimeter, we'd have to take that into account. But we don't need to worry about the Q for the calorimeter because the problem said ignore the heat absorbed by the calorimeter. All right, so Q for the object is negative 1,200 joules. So now, what is our Q formula for the object? Well, it's the same as the Q for the liquid. It's mass times C times change in T. But this mass is the mass of the object, whereas this mass was the mass of the liquid, right? So you want to make sure when you're finding the Q, whatever you're trying to find the Q for, you need to use the mass and the little c and the change in T values for that particular substance, right? We used all the liquid values up here to find the Q of the liquid. Down here, we need to use the object values in order to use the Q formula for the object. Now, we're not looking for the Q. We already know the Q, right? We just calculated that. But what the problem asked us for was what's the C of the object, the specific heat capacity of the object. So we're going to rearrange this equation and solve for C. And we divide both sides by mass and the change in temperature to get that the C of the object is equal to the Q of the object divided by the mass of the object, right? The mass of the object times the change in T for the object. Right, just putting object down there so we're clear. These are specifically the values for the object. And so we just plug those values in now. What's the Q of the object? Negative 1,200 joules. What is the mass of the object? They told us it was 45.9 grams. And what's the change in T of the object? Well, the object started off at it had a final temperature of 26.9 degrees Celsius. That's our final, minus what it started off as, which was 89.7 degrees Celsius. And so that's going to give us a negative change in heat value, change in temperature value. And when we plug all of those into our calculator, we get a value of 0.42 joules per grams degrees C. We get that as our specific heat capacity for our object that was of unknown composition, right? 0.42 joules per grams degrees C. Now, you'll notice we had a negative Q right here, and we ended up having a negative change in T, so the negatives canceled out. We had a positive value for our specific heat capacity. That will always be the case. So if you don't get a positive value for that, you did something wrong somewhere. So that's just something to be aware of. All right. So 42.42 joules per grams degrees C. We could actually look back at our table and see, is there anything that has a specific heat capacity of 0.42? It's close to nickel. It's close to iron. It's a little bit less than that. So you know, it could be a metal. The object may have been some metal, maybe containing those substances in composition of a solution, a mixture. There we go, of metals versus just being one made of one complete metal. All right. Well, that's how we figured out the specific heat capacity. Those are the formulas that you're going to need for that. And so make sure you know these Q formulas that we've begun to use here. We've given you 3 so far. Just to review, what are the 3 that we've given you? I say we because he gave them to you in the book as well. So Dr. Weil has given you the same ones. This is the Q of the liquid times the Q of the calorimeter, plus the Q of the calorimeter, right? So that's what negative Q object actually is. We were just able to ignore the Q of the calorimeter. And then we also said the Q of the calorimeter is equal to capital C, the heat capacity of the calorimeter, times change in T. So 3 Q-related formulas that you'll need to know in order to do problems that I give you over this material. Okay? As always, let me know if you have any questions.